Thank you, Ronald, and thank you, Ben, for this opportunity to speak. And thank you all for joining. It's really a special pleasure for me to present at a sustainable energy industry seminar because, as Ronald mentioned just a few years ago, I was a student in this class, and I found this class to be one of the richest and most rewarding educational experiences of my time as a grad student at UC Davis. So I hope today you all in this session find a fraction of the value that I found in this experience when I was in your shoes just a short time ago. Today, I'll be speaking about repurposing used batteries in stationary energy storage systems as a means to enable the transition to renewable energy and electric transportation. First, though, I'll reflect briefly on how my career began, and then I'll explore a few key energy industry trends underway today as they relate to this topic of battery reuse. I'll also share a bit about Repurpose Energy's work in this space, all the while sprinkling in some of the insights I've gained along the way. So, as an engineering student at the University of Illinois, some of my trusted mentors planted in my mind the idea that management consulting would be a great way to start my career. They convinced me that I would be learning a ton by constantly facing new challenges. I'd work hard, but it would be rewarding. And if I hated it, then new doors would open up. So I went for it and took my first full-time job as a management consultant at KPMG in Chicago. And about 6 months in, I was working on a long-term project with a big project team for a massive medical device conglomerate that was trying to untangle all its IT systems so it could spin off its biopharmaceuticals business to the highest bidder. So I classically felt at age 22 or so like a cog in a massive machine, and everybody around me seemed to be directing all their efforts at bringing value to shareholders and none of their efforts at bringing value to society. So I was pretty disillusioned, but I had this budding passion for renewable energy and climate change mitigation that was consuming pretty much all my time outside of work. And the firm did lots of work, lots of consulting in the electric utility sector. So I thought maybe that's a good way to more closely align my personal interests with my work at KPMG. So I went on to do a lot of work for Exelon mainly, which is the largest regulated electric utility in the country by some measures. And those experiences taught me a lot about investor-owned utilities incentives, namely to reduce operating expense at all costs, and then to inflate capital expenditures as much as the regulator will allow so that it can enjoy its regulated rate of return. However, that experience at KPMG didn't really satisfy my desire to be at the forefront of this critical transition to a decarbonized electric sector. And so I looked for new doors to open, and more or less as promised by those mentors of mine, I got a fellowship from UC Davis to join their energy systems program as a graduate student and study the economics, policy, engineering, and business of clean energy, which really kicked off a great new phase in my life. And as a student of energy systems, I developed a deeper understanding of what it will take really to decarbonize not only our electric system, but broader swaths of the economy. It became clear that there is no silver bullet, but there is a pretty robust playbook. And that playbook includes, of course, deploying renewable energy at an unprecedented rate, expanding transmission capacity, and also increasing interregional coordination between buyers and sellers of electricity, increasing the flexibility of demand through demand response, for example, storing energy at massive scale, and then extending the benefits of this decarbonized electric sector to the transportation sector by electrifying light-duty vehicles and buses, for example, and also to the building sector by electrifying low-grade space and water heating to start. And then layer on some energy efficiency, and we're well on our way to decarbonization using only existing technologies. So this plan, with all its faults, made me hopeful, but I was also overwhelmed like many grad students, I was struggling terribly to find some focus. And so over time, I dabbled mainly in these three areas highlighted here. I did some grid modeling to weigh the trade-offs of different mixes of renewable energy. I researched EV markets and the impacts of EV charging on the electric grid. And I became especially excited about the burgeoning energy storage industry. I saw market projections like this, explosive growth projections like this one from GTM Research, which suggested the energy storage industry was small at the time, around 2018, but growing dramatically. And thanks to the falling costs of renewable energy, lithium-ion batteries, and aggressive policy targets, this seemed to me in 2018 to be an industry that was just beginning to mature, and therefore an industry that I could possibly positively shape in some way with enough time and with enough focus.
Ryan, I want to just interject for just a second. We can't see your slides if you're progressing them. We still see the title slide.
Okay.
So you mentioned, referenced a couple things, and that's what I think we all clued in a little bit, that we're missing that. So.
Okay.
Maybe sometimes if I stop share and then reshare again, it works.
All right, let's try that.
You also need to make sure you've actually like clicked on the PowerPoint window itself or screen, and then, I mean, is it moving on your end or?
Yes, it is.
Oh, that's weird.
If you have a Mac, that's what happens to me sometimes too. There you go.
Now
Now it's working.
Yeah, now it's
Now you're seeing. Okay. All right.
We missed all the animations though.
I'll give you a little run through. As I mentioned, here are the principles of decarbonization I talked through, and then this is your basic up and to the right projection for market growth. So that brings us here. So you're all seeing a slide by Irina, right? According to the top right.
Yes, correct.
All right. So I was getting really excited about the energy storage market and increasing my focus on this space over time. Also,
I think Ryan might be frozen.
Yeah, Ryan, you froze there. You're getting to the really exciting part. You were deciding to focus, and then we lost you. So, can you?
Oh man, let me try to call in perhaps so that the audio connection at least is more stable.
Okay. I mean, this was the first time I think
an issue for me. I apologize.
Yeah, this was the first time this happened, so you could try again.
You could also try turning off your video, Ryan, just for preserving some bandwidth. It was the first time your voice had cut out.
All right, I'll turn off my video with any luck here. All right, I stopped my video. Does that help at all?
Yeah, I think we can still hear you. So we'll let you know if you pause.
Okay, thanks. So projections like this one, hopefully shown here now,
Yes,
suggested not only explosive growth, but also that small scale batteries or behind the meter batteries installed alongside rooftop solar might account for over half of all energy storage deployment on a global basis anyway. Now, behind the meter solar and batteries clearly have some very real challenges and disadvantages, but like many, I grew pretty enamored with the idea of a radically more democratized, decentralized, and potentially more resilient kind of electric grid architecture than the one we have enjoyed historically. And interestingly, at this time, around 2018, California was quickly becoming one of the hottest and largest markets for behind the meter solar and energy storage in the world. So I set out to do some case studies on this phenomenon to learn what was driving the trend of behind the meter solar and batteries. I did case studies on the the solar and storage economics for supermarkets, for example, but also hotels, homeowners, restaurants, schools, you name it. And in a nutshell, this is what I found. Until a few years ago, electricity prices consistently peaked in the afternoon when the sun was out. And net metering policies were very generous. And at one point, there was a subsidy, an additional subsidy for solar PV called the California Solar Initiative. So a supermarket in PG&E territory, for example, could earn a pretty good return by installing rooftop solar, and there wasn't really much need for energy storage. So the energy storage market remained negligible throughout the 2010s, really. But behind the meter solar deployment exploded in California throughout that decade. And utility scale solar deployment expanded just as rapidly at the very same time, until suddenly California was less than half of the way to its now 100% clean energy goal. And already the state had installed so much solar that it didn't really know what to do with it. So electricity prices began to consistently peak in the evening as the sun was setting. The California Solar Initiative subsidy is now long gone. Net metering is being slowly reformed to reduce cost shifting. And these changes, while necessary and warranted, are cutting financial returns from installing solar on supermarkets, for example. And these changes are also amplifying returns from adding energy storage to such solar projects. So stationary batteries, I learned, were quickly becoming a sensible investment for large energy consumers and others. But I wondered, just because a supermarket can benefit financially from adding energy storage to their rooftop solar, does that mean it is benefiting the environment? Does that mean it's reducing emissions by adding energy storage to that solar project? And I found essentially not exactly. So let's now look at the greenhouse gas benefits of energy storage for behind the meter solar and storage in California. To illustrate this, let's look at the greenhouse gas benefits of new lithium-ion batteries specifically installed with solar PV at commercial buildings in California. So here we have the annual mitigated greenhouse gas emissions in year 1, 2, 3, out to year 10, from using the batteries to displace generation from natural gas power plants. In terms of kilograms of CO2 equivalent per kilowatt hour of energy storage capacity. And these systems are typically warranted for 10 years. So that's why I've extrapolated to year 10. So to qualify for a rebate from the Self-Generation Incentive Program, or SGIP, which is a critical driver of the economics for energy storage, the operator of the energy storage system must prove the system is mitigating at least 5 kilograms of CO2 equivalent per kilowatt hour of energy storage capacity per year. And this is a relatively new rule. But luckily, the CPUC has issued some reports saying they think these batteries will mitigate around 10 kilograms CO2 equivalent per kilowatt hour per year, thanks to new electricity rates that I mentioned with the evening peak prices, which is pretty good news. But the bad news is that these mitigated emissions of around 10 pale in comparison to the upfront emissions which result from producing the batteries in the first place. Average production emissions are around 160 kilograms per kilowatt hour for the two most common types of lithium-ion batteries, NMC and LFP. So you need to operate the batteries well over 10 years just to get any net emissions benefit. So to reiterate in this context, the life cycle greenhouse gas benefits of new lithium-ion batteries are slim to none. And when I first put this together, I was confused and pretty devastated. I was confused because everyone around me seemed to agree that lithium-ion batteries were a phenomenal solution to short-term renewable energy storage on the path to grid decarbonization. And I was pretty devastated because I realized we need to do much better than this status quo to truly decarbonize the electric sector, to make this transition to renewable energy truly sustainable. And around this point in my journey, I had the opportunity to intern at the California Independent System Operator, which, as many of you may know, operates transmission infrastructure and wholesale electricity markets for most of the state. And this experience, while brief, allowed me to gain a fresh perspective on the myriad challenges of grid decarbonization, and in particular, the CAISO was struggling at the time and still does struggle with excess solar generation. And here is that problem summarized. When I was at the CAISO in the summer of 2018, curtailment of renewable energy was kind of the talk of the town. At that time, a clear trend was emerging. Every spring, the CAISO would pay operators of solar farms primarily not to generate their zero marginal cost, zero emission electricity. And every spring since 2017, CAISO set a new record for curtailment of renewable energy. Last April, for example, over 300,000 megawatt hours of renewable energy was curtailed, and that could theoretically power hundreds of thousands of homes continuously throughout that month. And one can fairly debate whether renewable energy curtailment is a feature or a bug of a grid powered by intermittent renewable energy. But in any case, in these simpler times before public safety power shutoffs in 2019 and capacity shortfalls causing rolling blackouts in 2020, oversupply of renewable energy was one of the biggest issues CAISO faced. And so they published these solutions to managing oversupply, which remain on their website to this day. And these solutions map very closely to the principles for grid decarbonization that I shared earlier. They include, first and foremost, in the top left, energy storage, as well as demand response, regional coordination, which was also a big push happening at that time, and so on. But everywhere I looked, all I saw at that time was energy storage and the mission critical need for energy storage. CAISO's solution was to, quote unquote, increase the effective participation by energy storage resources. They mean participation in wholesale electricity markets. The National Solar Trade Association, SEIA, was saying the solution was the, quote unquote, cost-effective integration of storage with solar. And so while at the CAISO, I doubled down and focused as much as I could on understanding the emerging role of energy storage in wholesale markets. I learned about some of the barriers and opportunities ahead of utility scale battery operators. I supported a stakeholder initiative to draft new policy around the use of energy storage as a transmission asset. And I supported the design and implementation as best I could of some new market rules to enable behind the meter energy storage to more effectively participate in these wholesale markets as a demand response resource. And at the end of my internship, I returned to Davis and connected with Professor Jaewon Park, who had been researching the reuse of electric vehicle batteries in stationary energy storage, among other topics, since 2010. And after years of work on one particular grant from the California Energy Commission, he and his team were just about to install their commercial scale demonstration of a second life energy storage system. And for this demonstration, they got their hands on around 15 Nissan Leaf battery packs that had been retired. They disassembled them, tested them, and reassembled them in a shipping container, essentially, at the campus winery, which is pictured here. And for the last couple of years, they've been basically charging those batteries using excess generation from the facility's rooftop solar array during the afternoon, and then discharging the batteries in the evening when electricity is again more expensive and also more polluting, to reduce the evening energy use of the facility by over 40%. And After 1 or 2 meetings with Jaewon about this concept, I was intrigued, and I began to research the potential of this concept. And I'll share some of my most surprising findings during this early research on the potential of battery reuse. One of the most surprising of those findings was this simple but important plot. And basically what it shows to me is that despite the billions of dollars being poured into energy storage and that explosive market growth we talked about at around 40% per year, global markets for stationary batteries here at the bottom look like a flat line at 0 compared to global battery demand for electric vehicles. In other words, by the end of this decade, we will retire and could repurpose enough electric vehicle batteries every year to meet 100% of our stationary battery needs. And this game-changing finding of my early research really shaped my perspective. Another finding I'll share is that all these lithium-ion batteries are difficult to recycle. In fact, lithium-ion batteries have been landfilled or stockpiled historically because of the expense and the difficulty of lithium-ion battery recycling. And recycling rates are going up, but the state legislature, the California legislature, wanted to be sure this trend did not continue as electric vehicles took off. So they passed a law which basically set a goal to ensure 100% of electric vehicle batteries are recycled or reused at end of life. And just to elaborate for a moment on the challenges of recycling an electric vehicle battery pack costs typically over $1,000 due to, among many other reasons, the relatively diverse and low value material composition as compared to lead acid batteries, for example, which have very high recycling rates. And the solution to this challenge of recycling, at least a partial solution, seemed to me to be battery reuse, given that 70% or more of a battery's capacity typically remains after its useful life in a vehicle. And so my research continued, and I crafted and honed a story about the potential of EV battery reuse. And that was the story, essentially, that we took out of the lab and into the real world to form a startup company, Repurpose Energy, that would repurpose EV batteries to create more sustainable, more affordable energy storage. And I mean more sustainable, not just because we extend the life of these existing assets, but also because we mitigate wasteful and unnecessary emissions and mining of new battery materials for new battery production. So this is a story we took on the road in 2019. We started with, as Ronald mentioned, a competition called Big Ideas, which helped us demonstrate the potential social impact of our venture. Then we went on to UC Davis Big Bang competition, which was more of a business plan competition, which allowed us to demonstrate the financial viability of our venture. Then we won a grant from the National Science Foundation to perform what they call customer discovery. So we interviewed over 100 potential customers and partners of the venture to hone our value proposition. And we also joined the Clean Tech Open Accelerator program to flesh out and stress test our plans. And we had some success in all of these efforts, and we won some grants to keep the ship afloat, and things were off the ground. So that is really how Repurpose Energy was born. I've never worked harder, I think, than that year, 2019, to get Repurpose Energy started. Made very little money, struggled with immense uncertainty, but I've also never been happier because of the profound opportunity I felt we had to make an impact, the passion I had about our mission, and the purpose I found in our work. In fact, I haven't talked about this publicly, and I'm not sure even my co-founders know about this, but the truth is the origins of the name Repurpose Energy with a capital P lie not only in the fact that we repurpose batteries, but in the profound sense of purpose, of meaning that I found in our work. And that's still my primary motivator today, not the promise of a payout upon exit or the freedom that comes with quote unquote being your own boss, but truly the deep belief in the value of what we're doing. So if I have enough wisdom to impart any career advice today, it would be that if you have a job that's not aligned with your values and a job that consistently feels like work rather than a source of purpose, look for ways to transition. Ideally, look for ways to transition that allow you to use the skill sets you've developed and maintain the momentum you've generated thus far. And ideally, don't transition into a role that doesn't allow you to support the basic financial needs of yourself and the people who count on you, but do look to transition into a role that gives you reason to wake up every morning and make the best contribution you can make that day. And with that said, let's delve a little deeper into the role repurposed energy plays in this industry today. So first, I think it's useful to understand a bit more detail on energy storage, and specifically its components. Batteries are not energy storage systems. Batteries are just one component of an energy storage system. You also need a battery management system to monitor temperature, current, voltage, et cetera, and ensure the safety of the batteries primarily. You also need a thermal management system to control temperature, which again is critical to safety and also mitigates battery degradation. I'll add, you need fire suppression systems typically to get projects permitted. You also need an energy management system, which is essentially a computer to dispatch the batteries appropriately, charge and discharge them such that the financial benefits to the customer or the owner are maximized. And lastly, an inverter to basically convert power from DC from the batteries to AC for the grid. And what's in this box is basically what's in the boxes shown on top, these complex subsystems of hardware and software. But you also need typically to offer some custom design services to make the project happen. You need to finance the project, permit and interconnect the project, install the system, and then operate and maintain it. So energy storage systems are not just batteries, they're complex systems of hardware and software and services, which all need to be packaged together to generate value with those batteries. And I mention this because as a very small startup company, we can't really do all of this effectively. And so we have to focus. And so our focus has been on a few things that we feel will allow us to safely and efficiently redeploy used batteries for 7 years or more. And our focus begins with rapid battery testing. So we use machine learning algorithms trained by many tests to measure the state of health of a battery in about a minute as opposed to several hours. This allows us to reduce our costs of repurposing. We then reassemble the batteries into new circuits such that discrepancies between batteries that are in the same circuit, discrepancies of internal resistance and capacity, for example, are minimized. And this basically, again, promotes safety and efficiency. We then re-equip the batteries with a new battery management system, again, for safety. We're also working on a non-destructive battery fire suppression system, which essentially will detect battery failure before thermal runaway and catastrophic failure occurs, and then deploys in order to mitigate the fire without harming any of the equipment that hasn't failed. So this is an innovation we're working on again to enhance the safety of battery reuse. So this brings us to 2020, which was a bad year by nearly all accounts, but not so much for clean energy. Solar and wind were notably resilient to the impacts of COVID. Around the world, EV sales were not as impacted as other new car sales by the pandemic. And 2020 also brought a flurry of new policies and plans. 100% clean energy targets are now the norm. They're coming from local governments, state governments, utilities, and energy buyers. And on the electric vehicle side, California now plans to phase out internal combustion engine sales by 2035. Other states are likely to follow, and other countries are setting similar targets to accelerate the transition to electric vehicles. Perhaps the starkest contrast between the last few months and the preceding years is that the stance of the new presidential administration has changed dramatically, and the Senate Majority Leader, I would add. So Biden has announced ambitions to entirely decarbonize the electric sector, to transition the federal government's vehicle fleet to an electric one, among many other announcements and targets. 2020 was also a pretty good year, all things considered, for repurpose energy. We gained our first private investment in February of 2020, and we won a $3 million grant from the California Energy Commission in April of 2020 to further our work. And with those funds, we're now working on a project similar to the winery commercial scale demonstration I mentioned, where we will install around 75 Nissan Leaf battery packs at a grocery store to again store its excess solar energy, reduce its electricity bills, and provide 24 hours or more of backup power to its critical loads. And backup power is really important to this customer because they have really suffered from the recent public safety power shutoffs. This results in food spoilage and huge loss of revenue and high costs for grocery stores. Some other goals of this project include measurement and reduction of battery degradation rates to prove battery second lifetime, and also to demonstrate the cost advantage of new battery alternatives. So with this product launch, we hope to kick off a series of many more projects like it and deploy Second Life energy storage across the state. And to do that, we hope to deliver this value proposition to our customers. We hope to facilitate achievement of their sustainability initiatives, to provide resiliency in the face of increasing outages, and to deliver utility bill savings. And if we execute well, I wholeheartedly believe that by 2030, Second Life batteries can contend with new lithium-ion batteries as a primary enabler of the transition to renewable energy and electric vehicles. Thank you. We have some time left. There are a few more slides I'd like to speak to. We can also take some questions, whatever you think would be best, Ben.
Well, first of all, thank you, Ryan, for making this presentation, sharing this with us, and of course, preparing your case challenge that you're going to share with the students, go over with the students a little bit later. Let's give you some snaps for that today, and applause. I think we have a little time for, unfortunately, I got logged off accidentally, so my chat has disappeared, so I don't have all the list of questions that I've already seen. There were some questions I saw about the dynamics of your customer being the grocery store and who actually owns whether they own the commercial property, and so can they own then the battery and solar or what's the dynamic of that ownership of those assets? I think there was a question about that, but I think we'll have a little bit of time, and we'll see, maybe if you've got a question, put it in the chat that I haven't seen, and because you're gonna have to repeat that question for me so I can see it and I can bring it up. Otherwise, why don't you answer that general question, and then you can speak to some of the additional slides you might have.
Perfect. Yeah. Ownership, customer segmentation, and in particular ownership when the commercial end user doesn't own the property. These are all good points. So I'll start with who is our customer. I mentioned this grocery store is the location of our product launch, and this grocery store is our customer. But in the future, our customer may be instead the developer of these solar projects. And we're working with one such developer on this grocery store project. And the reason making developers the customer as opposed to the grocery store may be more attractive is that these developers already have lots of experience with customer acquisition, project financing, permitting, interconnection, installation, and so on. Some of those suite of services I mentioned that are also required to get an energy storage project off the ground. So that's one point. The owner of the asset depends. If a grocery store, for example, has some capital budget or they have access to low-cost debt, they can buy the asset and then enjoy all the benefits that it provides. Typically, though, they'll also need to sign an O&M contract with us and or whoever's providing the energy management system to dispatch the batteries in order to actually gain value from the asset. Now, what if the grocery store doesn't own the property? They can still install energy storage, they can still buy the energy storage, but they do have typically appetite for shorter term lengths because of the uncertainty that comes with not owning the property you're on. What if your lease ends and you move? Do you lose out? And so those shorter term lengths are actually an advantage for us, that desire for shorter term lengths, because our products as compared to new lithium-ion batteries are lower cost, a lesser capital investment. And so those that have shorter time horizons benefit from a lower CapEx investment. So that's a bit of commentary on that set of questions.
Great, thanks. Another question, California obviously is your initial market, and there's a law that you referenced, the law that talks about kind of the need for either recycling or reuse, and that again helps with the value proposition. Are other state laws kind of moving in similar directions? Do you see is there a federal kind of momentum in a similar direction?
I have spoken with some people from out of state, Colorado, for example, who are working on projects to make recommendations to their own state legislatures on how to encourage battery recycling and reuse, basically how to address this tsunami of battery waste that will come as electric vehicles scale up and are retired. But they're basically waiting and watching California to see what California does and how it goes. And so I suspect, just like has played out in renewable energy and in other ways, California will move first in this respect on EV battery end-of-life management. Other states will follow, and then we'll see federal action last, would be my guess. But of course, I have no crystal ball.
Thanks. Meg put a question in the chat. I'm going to let her just go off mute and ask you that question directly.
Okay. Hi, Ryan. Good to see you again. So my question is just about, it's a very rapidly moving landscape, as we both know, in terms of both new players a lot of startups, also battery technology continues to develop, as well as kind of end of life technology. And I'm just wondering if you could share how you focus on needing to, or how you balance the need to kind of stay focused and make forward progress with projects you're already working on, and as well as the need to kind of stay updated and know what's going on and stay on top of everything that's changing.
Yeah, that's a great question. I struggle is the answer. I miss that about grad school, because in grad school, I had the luxury of being able to spend so much time reading and learning and exploring things out of curiosity. So I felt very much up to date on some of the key things happening in the industry. And now, as an entrepreneur and not a grad student, in particular as the chief operating officer of this small company, there are a lot of distractions, a lot more competing priorities. You know, I have to buy insurance for the business and do our accounting and HR and other things like that. And so there's just not as much time to stay up to date. And so it's a challenge, but I've gotten a lot better at prioritizing. And I would say enjoy your time as a student while you can, because it's one of the best times to learn.
Thanks, Ryan. So we got a question here about the cost of acquiring used Nissan batteries, and then kind of a reference to the Tesla batteries as well. And so I assume there's going to be kind of differences among the different battery types across vehicles. Again, probably difficult to keep up with it all, but I'll throw. So just there was a question about what's the cost generally of acquiring some of these used batteries. And I'll kind of just throw in, just because Tesla was mentioned, JB Straubel, the co-founder of Tesla, just started up a company. I think left Tesla and is starting up a company to work on exactly this kind of opportunity using actually Nissan Leaf batteries, I think, for stationary applications. So that kind of validates your business model and value proposition, but at the same time adds competition for used batteries. So what are the implications from the cost of one of your raw materials, if you will?
Mm-hmm. Okay, lots to unpack there. So when a Nissan Leaf battery reaches end of life, whoever owns that battery or has responsibility for disposal has a choice. Like I mentioned, you can pay to recycle, probably $1,000 in the case of a Nissan Leaf, including transportation, or you can sell it or give it away to someone with interest in repurposing it and giving it a second life, like us. So we've received lots of donations of electric vehicle batteries over the years. Usually we have to pay some small amount, and that amount at times is higher than you'd expect, higher than the actual value of the battery, I would argue, because there are a lot of hobbyists and a lot of researchers with an interest in Second Life that are creating a pretty significant amount of demand for used batteries compared to the supply today. And I think that will change dramatically in the future as that tsunami of waste crashes down on us, as I mentioned. But these days, we do typically pay for used batteries if they're suitable for our needs, which means they're relatively healthy. Redwood Materials, JB Straubel's company, to my knowledge, is a recycling company, not a reuse or repurposing company. And so lots of parties are getting into this space, and certainly the cost of recycling will probably, I won't say certainly, but they'll probably come down significantly over time with economies of scale and as innovation occurs. But at the same time, battery manufacturers are taking the high value metals out of their batteries year after year after year as much as possible to reduce the cost of new batteries. And so the less valuable the materials in the battery, the more expensive recycling is going to be. And so I think inevitably, for the foreseeable future, there will be significant cost to recycle a lithium-ion battery, and that will maintain some value proposition for repurposing.
Thanks. And thanks for that clarification too on recycling versus reuse, repurposing for JB's company. All right, another question about V2G. What is, with a bigger emphasis on V2G, what are the implications of that for the future of repurposing batteries for stationary? Because it's actually doing it within the vehicle, of course, so that's a competitive offering, but at the same time, it may accelerate the retirement of some of those batteries in the vehicles.
Mm-hmm. Yeah, V2G is a great topic to raise here. So I think the most important aspect of V2G related to this conversation is that it's basically a competitor of energy storage, because V2G is another source of the kind of flexibility on the grid that we'll need to integrate lots and lots of renewable energy. And because of the magnitude of energy storage capacity that is in an electric vehicle battery pack and will be available for essentially energy storage down the road, that may diminish the need for stationary energy storage if it's done at scale. And that's yet to be proven. I think it's pretty likely that V2G will begin to occur in a meaningful way. But I don't think, as the asker of this question mentioned, that automakers are going to explore battery repurposing as a secondary business anytime soon. In fact, at this point, they're pretty concerned about liability for battery fires, for example, that might occur in a second life energy storage system. They're keeping a tight hold on their IP, and they have their hands full with trying to make money on selling electric cars. That's a huge disruption to their business, and they're not really in the energy storage market. And so I don't see them taking an active role in battery repurposing in the near future. I think eventually they might make acquisitions or strike other forms of collaboration with repurposing companies, but that's a few years out, more than a few years out in my belief.
Thank you. Eric Johnson asked a technical question there, and I don't know if you see it in the chat.
Mm-hmm.
Do you want to comment on that?
Yeah, Eric's asking about basically how fast we charge and discharge the batteries. Are we using a C/10 charge discharge cycle? What's the depth of discharge? And I'll try to leave out as much jargon as possible. I think what's important here is that when a battery is used, it might, and let's say it could initially store 100 kilowatt hours. At the end of its life, if you charge it and discharge it really slowly, it might still be able to store 80 kilowatt hours. So it might have an 80% state of health. But if you need to charge it and discharge it really quickly, as you do in a vehicle, then it might be able to store only 70 kilowatt hours or less. So the state of health, the energy storage capacity, depends on how quickly you're charging and discharging the battery. And we charge and discharge much more slowly than vehicles do, which allows us to basically get more value out of these retired batteries. So that's what I'll say about that question.
Great. You mentioned you have some additional slides. I'm sure folks would be interested in any additional insights that you want to share with us.
Yeah, I'd be happy to. So the title of this talk was something like battery reuse as an enabler of the renewable energy transition and transportation electrification. And I did a lot of talking about how second life batteries can support the transition to renewable energy, but not a lot of talking about how this could enable transportation electrification. And so just one point to make on that, is that EV battery reuse can support a lower total cost of vehicle ownership for electric vehicles. And this is material because today, according to this survey by AAA, the total cost of ownership of an EV, excluding Tesla, which is important, is actually higher than the total cost of ownership for an internal combustion engine. And this is surprising because we're not talking about upfront cost here or the cost of a lease payment. We're just talking about fuel, maintenance, registration, depreciation, and financing. So this is sort of contrary to the story we often hear, which is, yes, EVs cost more upfront, but they are cheaper over time because electricity is cheaper than gasoline and you'll need to maintain it less. And it is true that, according to the survey, fuel costs are lesser and maintenance costs are lesser for an EV than an internal combustion engine. The killer is depreciation, which is highlighted here. That's over twice as much as an internal combustion engine for an electric vehicle. And this is because resale values and salvage values for electric vehicles thus far have been surprisingly low. And the low salvage value is because an auto recycler for an internal combustion engine car could get a few $1,000s for the engine and the transmission. But if they get an electric vehicle in their yard, instead of making $3,000 or $4,000 on that engine and transmission, they have to pay about $1,000 or more to recycle the electric vehicle battery pack that replaced it. And so this phenomenon really depresses the salvage value and therefore the resale value of electric vehicles, which is driving up the total cost of ownership for electric vehicles and making it, in some cases, higher than internal combustion engine cars. And so I would argue that there's an opportunity via battery reuse to increase the salvage value of electric vehicles and decrease the depreciation of electric vehicles, and therefore lower the total cost of ownership of electric vehicles for EV owners. And I'll circle back to one caveat I made, which is that this calculation excludes Tesla. And that's because Tesla is exceptional in this respect. Their vehicles are depreciating very little. There's a ton of demand for used Teslas. And I think this is because they're degrading more slowly. They have more range, so they're more valuable to people. And also there's just a lot of interest and excitement about Tesla. And so people that can't afford one, can't afford a new one, are in the market for a used one. And so it's possible that this trend or this difference here will change over time. We'll definitely see a reduced total cost of ownership for EVs over time. And I hope it goes in the way of Tesla. But in any case, there's a role for battery reuse to play as well.
Thank you for sharing that. And I think others are on the chat are also appreciative of it as well. And Meg, you had an additional question here. I'm just reading through it here. Do you want us to just talk it through? Go ahead.
Oh yeah, I can read it as well. So my question is that I understand that the depreciation is also higher because used EVs don't sell well in wholesale auctions for dealerships. Because I think dealerships have a hard time selling the used EVs because consumers are generally kind of mistrustful about the performance of used batteries. So I was wondering if that kind of skepticism about used batteries in particular, I think even compared to other used products, I was wondering if you think that is also a factor in second life storage, or how you kind of overcome that skepticism.
Mm-hmm. Yeah, great question. I would try to put a finer point on this total cost of ownership discussion by saying that I think the salvage value of EVs is depressed primarily because of the cost of recycling, but the resale value of electric vehicles is depressed primarily, I'm guessing, because of the skepticism from consumers about, I don't think it has enough range, I don't know how long it's going to last, et cetera. And so that skepticism, that uncertainty about battery performance and battery lifetime is definitely a challenge for us to address as well. And we're trying to address that with this grocery store product launch that we're doing. And I think we can also address it by offering customers pay for performance type offerings where they don't have to buy this thing up front with all the uncertainty that comes with how long it's going to last, et cetera. They can just pay for our performance, and we can make sure that we're replacing used modules as needed to maintain the energy storage capacity and the services that we promise. So those are some of the ways we're addressing that concern, that skepticism.